about efficient mining of frequent patterns on uncertain graphs. Introduction. The project is focused on the challenge of frequent subgraph mining on single uncertain graphs, which are graphs with edge uncertainty. In terms of support definitions, the project investigates two possible semantics, probabilistic and expected. They provide an enumeration evaluation technique for solving the problem with probabilistic semantics, as well as an approximation approach with accuracy guarantee for efficient problem solving. The algorithm is modified to tackle the problem with expected semantics by including checkpoint-based tuning and validation mechanisms. The topic is motivated by three major application domains, including the identification of functional modules and evolutionary conserved subnetworks from protein interactions network. Objective. The project's objective is to provide efficient algorithms for mining frequent subgraphs on single uncertain graphs, which are graphs with edge uncertainty. In terms of support definitions, the project investigates two possible semantics, probabilistic and expected, and presents an enumeration evaluation algorithm to solve the problem under probabilistic semantics. They also create an approximation algorithm with guarantee of accuracy for efficient issue solving. The algorithm is modified to tackle the problem with expected semantics by including checkpoint-based pruning and validation mechanism. The project intends to address the problem of frequent subgraph mining on uncertain graphs, which has received less attention than deterministic graphs, and to motivate through three diverse application domains, including bioinformatics and social networks. Requirements. The requirements of the project are hardware requirements and software requirements. In hardware requirements, we have operating system Windows only, processor i5 and above, RAM 4GB and above, hard disk 20GB and above. In software requirements, we have Python IDEL with 3.7 version. Algorithms used. To implement this project, we have used the following three algorithms. The first algorithm is enumeration evaluation. Enumeration evaluation is a straightforward approach to frequent pattern mining on uncertain graphs. It involves generating all possible candidate patterns from the uncertain graph and then calculating the probabilities. The algorithm generates candidate patterns by considering all possible combinations of edges and nodes in the graph. After generating candidate patterns, it estimates the probabilities by considering the uncertainty associated with the edges and nodes involved. The main limitation of this approach is its high computational cost, especially for large uncertain graphs, as it involves exploring an exponential number of possibilities. Second algorithm used is probabilistic evaluation. The probabilistic evaluation algorithm aims to efficiently estimate the probability of a candidate pattern being frequent in the uncertain graph. Instead of enumerating all possible candidates, this approach leverages probabilistic techniques to calculate the probability of each candidate directly. It uses mathematical tools like probability distribution and Markov chains to estimate the frequency of patterns in the uncertain graph. This method significantly reduces the computational burden compared to enumeration evaluation and is better suited for large-scale uncertain graph. Third algorithm is estimate evaluation. The estimate evaluation algorithm strikes a balance between the enumeration and probabilistic evaluation approaches. It uses sampling and statistical estimation techniques to approximate the probabilities of candidate patterns being frequent. Rather than exploring all possible candidates, it randomly samples a subset of candidates and calculates the probabilities based on the sampled data. By using statistical estimation, the algorithm can provide approximate results with a controlled level of confidence. This approach is computationally more efficient than enumeration evaluation and can handle large uncertain graphs while still offering reasonable accurate results. Methodology. To implement this project, we have designed the following modules. The first module is Upload DBLP dataset. The first module involves uploading the DBLP dataset. DBLP is a popular bibliography dataset in the field of computer science that contains publications and authors' information. The dataset includes various types of data such as author collaborations, paper citations, and co-author relationships. Uploading the DBLP dataset is the initial step in preparing the uncertain graph for further analysis. Second module is Generate Graph. In this module, the DBLP dataset is transformed into an uncertain graph representation. Nodes in the graph represent authors or papers, while edges represent relationships such as co-authorship or citation links. Uncertain graphs introduce probabilistic uncertainty in the form of edge or node existence probabilities. For instance, an edge between two authors may have a probability indicating the likelihood of collaboration. The generation of the uncertain graph is essential for subsequent mining tasks. Third module is run probabilistic frequent subgraph mining. Probabilistic frequent subgraph mining is the process of discovering frequent subgraph in the uncertain graph, considering the probabilistic nature of the edges or nodes. Frequent subgraphs are patterns that occur frequently enough in the graph, considering a user-defined minimum support threshold. The algorithm analyzes the uncertain graph and identifies frequent subgraphs that appear with sufficient probability. It counts for uncertainty while determining the support of the subgraph. Fourth module is run estimate frequent subgraph mining graph. Estimate frequent subgraph mining is an alternative approach to identifying frequent subgraph in uncertain graph. Instead of enumerating all possibilities, this method leverages sampling and statistical estimation techniques to approximate the probabilities of subgraphs being frequent. By sampling a subset of candidates and estimating the probabilities, the algorithm can provide approximate frequent subgraphs more efficiently than probabilistic mining. Fifth module is elapsed time comparison graph. The elapsed time comparison graph is a visual representation of the time taken by different mining algorithms, probabilistic and estimate, to discover frequent subgraphs in the uncertain graph. It helps to compare the efficiency and performance of the two approaches. The graph typically shows the elapsed time y-axis against the size of the uncertain graph, or the minimum support threshold x-axis, to assess how the algorithm scaled with varying input sizes and requirements. Execution. For the execution of the project, we need to open the code folder. This is the code folder. This is the dataset folder. To implement this project, we have used DBLP dataset. DBLP dataset contains information about authors who publish papers. For a single paper, sometimes there will be main author and co-authors who work combined to make one paper. So all authors are the vertex of the graph and edges will be given between main and co-author. And these are the main code file. This is run.batch file. Instead of executing our project in the command line interface, we have created Windows batch file to execute the project. Double click on run.batch file. This is the graphical user interface which we have created using the Tkinter library in Python. Using this GUI, we will interact with the project. Click on upload DBLP dataset to upload the dataset. Select DBLP open. So here we can see that the dataset is loaded. Now click on generate graph to generate the graph. So in above screen we can see graph generated from author and co-author details. So here we are having the author name and as well as the co-author name. So in this way the graph is generated. Now click on run probabilistic frequent subgraph mining and enter threshold value. So here I am entering threshold value as 3, which means from large graph I want to get all subgraphs whose edge is greater than or equal to 3. With 3 threshold we may get 13 graphs and each graph will display with a pause of 3 seconds. If we want, we can give threshold as 1 or 2 also, but lots of subgraphs will be generated. That is the reason I have given threshold as 3. Okay. So here these are the 13 graphs which will be generated. So each graph will be for 3 seconds, and here in each graph we can see the different names which are present here. So after these, so here we can see that we got the number of probabilistic frequent subgraphs are 13 and probabilistic computation time was this much. Now click on run estimate frequent subgraph mining to run estimate algorithm. So here also I am giving the threshold as 3. So here also we will get the 13 subfrequent graphs. And if so, here we can see we got the number of estimate frequent subgraphs was 13 and the estimate computation time was this much. Now click on parallel processing. So here also I am giving the threshold value of 3, so it will be the same. We will get the 13 subgraphs one after the other, and we just need to watch these graphs. So with parallel processing also, we got the number of estimate frequent subgraphs is 13 and the extension estimate parallel computation is 11.64. So with the estimate frequent subgraph and parallel processing, we got the 13 subgraphs only. Now click on elapsed time comparison graph to get comparison between both algorithms. So this is the comparison graph. X-axis represents algorithm name and y-axis represents graph generation speed. From above graph, we can conclude that estimate algorithm is 20% faster in execution and probabilistic algorithm is 40% faster and probabilistic algorithm is 50% faster compared to estimate algorithm. Now we will close the graph, and the final conclusion of the project is the project concludes that the methods presented for mining frequent subgraphs on single uncertain graphs are successful and efficient. The computation of #p-hat support is resolved by approximating the true value into an interval with accuracy guarantee. Computation sharing techniques are being developed for probabilistic semantics to improve efficiency. Unpromising subgraphs are trimmed and promising subgraphs are checked at checkpoints for predicted semantics using structure-based upper and lower bounds. Experiments on real-world data sets confirm the mining method's applicability. The project addresses the challenge of frequent subgraph mining on uncertain graph, which has received less attention than deterministic graph, and draws inspiration from 3 diverse application sectors, including bioinformatics and social networks.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.